finish this thing of expected sequences. So last time we were set up to prove, which probably we won't finish today, but if we had two functors, say f from C, no, well, from a derived category. I think I had them like this, from A to B, and G from B to C. Abelian categories. Then we had the corresponding derived functors from D plus A to D plus B. And we had the derived functor of this G from D plus B to D plus C. We have the composition of these two. These are exact functors, so we have the composition of these two guys are G, and we also have this functor, which is the derived functor of the composition of these two. And we've checked that if we have adapted categories for A and B, with the property that anything, a complex in the adapted category for A lands in the adapted category for G in B, then these two are isomorphic, and we gave an explicit isomorphism. But this, what we set up to prove is that we get, out of this isomorphism, we get a spectral sequence and this is the useful thing. So not about just this isomorphism of functors, but actually computing the homologies of the corresponding functors applied to objects. So whose E2 term is given by the Q homology of the, oh, well, I guess RQG of RPF applied to a complex A. And this spectral sequence converges to the homology of the composition, to the RP plus Q G composed with F of F. So this is what we set up to prove, and that's going to take some time. So this came from a spectral sequence whose E2 term is given by a bicomplex, a spectral sequence associated to a bicomplex that starts at the E2 term, and that in itself comes from a spectral sequence that starts at the E1 term associated to a filtered complex, and that's what I want to talk about today. But before we deal with that case explicitly, let's start with what is an exact pair, an exact couple. So definition, an exact couple is a pair of morphisms, well, a triple of morphisms, like this, with the property that any image is the kernel of the next morphism. So the kernel of alpha is equal to the image of F, the kernel of F is equal to the image of G, and the kernel of G is equal to the image of alpha. If we're given such a situation, and this is in an abelian category, these are all A and E are objects in an abelian category. If we're given that situation, then we can define D to be the composition of G with F. So this is an endomorphism of E. And notice that D squares to 0. Because this is just G composed with F, composed with G, composed with F, and the kernel of F is the image of G. So therefore here, in this composition, we're landing on the image of G, which is in the kernel of F, and this composition is 0. So this, whenever we have an exact couple, E becomes a complex with this differential. But we can actually play a little game, which is we can look at A prime, define it to be the image of alpha. We can define E prime. Should have said something before for general spectral sequences, but well, anyways. We can define E prime to be the kernel of G divided by the image of D. Now, alpha induces a map, alpha prime induces alpha prime from A prime to A prime. G induces G prime from A prime to E prime, because E prime, by definition, is a subquotient of E, and G is gives me a map from A to E. If I restrict it to the image of alpha, then I am landing on the kernel of the differential, so I can view it as a map from A prime to E prime. And F, well, but not really F. I only needed F defined on the preimage of alpha. So of alpha inverse induces an F prime from E prime to A prime. So we started with an exact couple, and I constructed a differential on this guy E. I looked at the homology of E, of that differential, and I get a new object. And I look at the image of this map alpha, and I get a new object A, and I've gotten a new exact couple. Which again, I can just repeat this process and I get a new complex E prime. I can continue this process and getting new complexes at the bottom. So this way, from an exact couple, so from an exact couple, I obtain ERs, ARs, and maps AR, alpha R to AR, FR, GR, oh, the other way around, FR, ER. This is the guy that I'm interested in because this guy becomes a complex, has a differential, DR, and the homology of ER respect to DR is ER plus 1, which is the datum of a spectral sequence. I haven't, so when I define spectral sequence, I define it also with the limiting complex. I'm not telling you what the limiting E is, but that's irrelevant. So the datum here is just this sequence of complexes ER. I also define them to be bigraded. That's also irrelevant, and it's cluttering in the notation. So let's not worry about P and Q that I'm going to add in the end. Okay, so this is just a statement that if you give me 2 objects and 3 morphisms in an abelian category with this picture, then you get immediately a bunch of complexes that you construct iteratively this way. And each complex is the homology of the previous complex. Now, we can look at we can make the following definition. So we notice that we can define the following. We can look at BR to be the image under. Well, let's do the next one. Let's suppose that I defined BR already, and so I look at this as this GR of alpha R. I think I'm using upper and lower indices everywhere, I guess. I'm going to use upper indices because it's useful for this one. And lower indices for the other ones. So this is of A. I should have written there A sub R, but it's the same because all of those are induced from the original A that I started with. So I guess A is going to be A1. So this is inside of ER. This is inside of ER. But yeah, so let's be more precise. Let's be more precise here. I want to define something more concrete. So I want to define the following sequence. So I'm going to start with 0, which is going to be included in B1, which is going to be included in B2, and so forth. It's going to be included in BR, and this increases. And then these are going to be included in ZR, which is going to be included in ZR minus 1, which is going to be included in Z1, and this is going to be the whole of E1. Because I could start with this being equal to 0 as well. In such a way that ER is equal to ZR divided by BR. So in particular, I want this ZR to be the kernel of GR minus 1. Oops, I want the other way around. I want E. So if I make this guy to be 0, then E1 by definition is going to be Z1 divided by B1. Yeah, so I guess the ordering is correct there. So for R is equal to 1, this is just the definition. And then for R bigger or equal than 1, this is what I want. But for R bigger than 1, this is what I want. So the point is that all of the ERs that I started with, so in particular all the ER for every R are subquotients. Of E1. And E1 is what I started with from I started from an exact couple. And I make this E to be E1. And I constructed all of the next ones iteratively, but I'm going to check that this actually happens there. So what is BR? And this is just by construction. At each step, so I started with B1 being 0. That's just the definition. And Z1 being all of E1. Again, that's just the definition. So Z1 is just all of E. And B1 is 0. But then, what is the image of the differential? Right? So what is B2? Because what I want is that E2 should be the homology of E1, which should be the kernel of the differential modulo the image of the differential. So what is it? What is that image of D1? Well, the image of D1, we checked it here. Our differential is the composition of F and then G. And the image of G1, therefore, is alpha, is alpha of A. So the problem is that alpha of A lands here, and then I just map it by G. Let's look at what is B3. So this should be inside of B3. Well, how am I going to construct now the next differential? Well, the next differential is, I define this guy is my A prime, which is A2. And now B3 is going to be defined out of the next, is going to be the B2 for the corresponding exact couple, where I start with A2, A2, E2, like this. And now I am going to have like G2, F2. And my new alpha, 2, which is just the same alpha that I had before, but now I apply it twice. That's why the upper index is probably better. So this B3 is now going to be G of alpha squared, and so forth. So all of these guys, BRs, BR plus 1, is equal to G of alpha R of A. And what we checked is that this guy is included in BR plus 2. Or probably better to make it BR inside of this. How about the ZRs? Same argument. So for ZR, you do the same. So the ZR is just the kernel of the differential that you can check it immediately that it's of this form. Is F inverse of alpha R minus 1. A. And this guy is included in ZR minus 1 and so forth. And the fact that this is the kernel is just because, well, the differential is just G composed with F of this. So if you plug it in with G composed with F on this, you're going to check that this guy is of the form, well, G composed with F on this, it's going to be landing in the kernel of the map, in the image of the map alpha, which is just 0, therefore, in this here. Okay. Yeah. But the whole point is that these guys, as written, they are all inside of E1, which is the original E. Okay. So now, whenever I have an exact couple, I have an explicit spectral sequence. Well, although I haven't constructed the final complex, but that's irrelevant for a second. And I also haven't given you the grading. So let's deal with that. Let's suppose now that A and E are complexes. So that they have a differential themselves. Because I constructed a differential on this E. I constructed a differential on this E, well, actually, by applying this composition. So let's start with a different situation now. Right. So let me start with the situation where this abelian category is a category of complexes. So let's start with A being the category of complexes in a different abelian category. So probably something like this. And this is also abelian. I'll forget about the grading for a second. But the point is that if we have an exact I guess I'll do it like this, but I'll change that notation in a second. Suppose that this is exact, and let's suppose that this is injective. So here, I can just immediately put it like this. Let me write it like this. Suppose that I have an injective map. This is all we'll need. And A is a complex. I think this is all I need. So this is an injective map. I have the quotient. I'm in an abelian category of complexes. And what we know is that we have a long exact sequence in homology. But we can write that sequence if I disregard the gradings. How does that look? I have my homology map. I have my homology map. I have the homology of the quotient complex. Let's analyze what are these guys. So if I have a map from A to the quotient, which is just the map induced by this quotient map in homology. I have a map from A to A, and that induces a map in homology. It's this alpha star, if you wish. I'm going to forget about this star here, and this is pi star, and I'm going to forget about the star in a second. But this one here is coming from the connecting homomorphism that I get in homology out of the snake lemma. So this guy, if I remember the gradings in homology, this guy carries a degree shift, which I'm going to disregard for a second. So this is the full homology, and the full homology. But the fact that that in homology I get a long exact sequence means that this is an exact couple. Or pair. So I'm going to call this guy G, I'm going to call this guy F, and I'm going to call this guy alpha, as I did before. So whenever I have an injection of complexes, I get an exact couple this way. And therefore, I get a spectral sequence. So this gives rise to a spectral sequence, ER, which is the associated spectral sequence to that exact couple. Again, the differentials are very, very explicit here. In particular, E1, the first term that I started with, is the homology of the quotient complex. And the differential is just the differential induced from the differential in G. Here, G is the differential of A. It's the differential of the quotient of A by alpha of A, but that one is induced by the differential G of the original complex A. Okay, so that's my first guy here. And you see that what is the differential on E1? E1 has a differential. And again, by construction, this differential is constructed, is the composition of the map that is just the quotient map of the quotient map in homology with F, with the connecting homomorphism in homology. This is given by Snag Levy. So you already see that if I want to compute the differential of an object in E1, which again E1 can be realized inside of A, or as a quotient of A, of a subquotient of A, then what I can do is I grab an element in E1. Well, it is the homology of A divided by alpha A, so I can just pick a representative in A. And since I need to compose these two things, well, the first thing I need to apply is this one. Because remember, the differential D is G composed with F. So the first thing I need to apply is F, which is the connecting homomorphism homology. And how do I do this? Well, I just take the derivative, the differential in A. That's how we compute the connecting homomorphism homology. We pick a lifting, we take the differential there, and then we map it to the quotient map. So that's exactly what we're going to do in E1. And I'm going to write this explicitly in a second in the case that I'm interested. So, but you see that computing homologies on this spectral sequence is going to involve lifting to our original complex A and taking the differential on A itself. So how do these differentials and how do these BRs and ZRs look like in this picture? Well, I have them explicitly there, but so now let's see. So our BR, which remember this is G of alpha R, is the kernel of the differential first of all. This was G of alpha R, but it's the kernel of the differential in degree R minus 1, if I'm not wrong. Okay, and what is the kernel of that differential? Well, it's something that when I apply D, I land in 0. But G, if you look at G, G is the quotient map by alpha A divided by alpha A. So you see that this thing here ought to be alpha R minus 1 inverse of D of A. Because, well, D of A is what gets killed here. This alpha A. Well, this is the image of the differential. Let me write them and then we'll check these things. So this ZR is F inverse of alpha R minus 1. And I claim that in this situation, this guy here looks like, rather, this looks like D inverse of alpha R minus 1, alpha R. And ER is just the quotient of these two. Okay. Let's work out the example that I'm interested in, which is the following situation. Definition. A filtered complex is a complex A. Well, it's a filtered object in the category of complexes. So I have a complex, which is my cochain complex in a abelian category A. And I have a decreasing sequence of subcomplexes I will require it to be, this is the only condition. So the condition is that the differential on FP, they are all inside of A. So that's one condition. They are all subcomplexes of A. So in particular, the differential of FP of A is inside of FP of A. And this is the differential of the complex A applied to FP of A. So that's a filtered complex. Okay, so examples of filtered complexes. These are essentially examples. These are essentially all the examples we'll need. Suppose that you have a double complex. And these are cochain complexes, so the differential is increases degrees. So the differentials go like this. Let's call this complex this. Then the total complex is filtered. Then we have a total complex. This guy is filtered. And Fp of C dot, well, it has two filtrations. We can pick the filtration where we pick everything above the pth row. And you see the differentials, well, the horizontal differential goes this way, the vertical differential goes this way, so preserves this whole picture. Or we could pick everything that goes on the right of the pth column. And both are good filtrations, so we can just look at this and look at this by definition being the direct sum. It depends if you're looking at tot with the sum or tot with the product. Same thing you're going to have to take here. But then this is C ij, where I is bigger, doing the column, so the row. So this is where j is bigger or equal than p. And if I fix the degree, so let's say that I look at Fp of Cn, then I'm going to take the sum of I plus j is equal to n. But I'm not going to be worrying about the total degree, about the left degree here. And it's clear that D preserves this because D of the component in degree ij goes to I plus 1j, which still has j bigger or equal than p, or goes to I j plus 1, which still has j bigger or equal than p. So that's a filtered complex. Another silly ones are given by inclusions. If you have a complex, say, I think we've seen this already, a I minus 1 to a I minus to ai to ai plus 1, plus 2, and so forth. Then I can write an injection from a different complex into this, well, by looking at the kernel. So if I want to map 0 here and make this diagram commute, this is going to go to 0 here, so there's no problem. But then I would want to have ai plus 1 here, and the identity here, and ai plus 2 here, and the identity here. But then this composition here should be equal to this composition there. And to have that map commute, I'm going to look at the kernel of, probably I'm doing this the other way around. Let's see, inside of here. Sorry, kernel of GI inside of here. So that guy, this composition here goes to 0. And this composition here goes to 0 because this is just di the map. And this composition here goes to 0, and this composition goes to 0, so everything here commutes. So this is a subcomplex of this, and this gives you a filtration stopping on E. So I can look at this complex inside of this complex. That's a filtration. I mean, of course, you can iterate this process by looking at the kernel of the next one for I plus 1, and that gives you a complex inside of the next one, inside of the next one. So this is an increase in filtration. And I think I've only defined decrease in filtration. So let's do a decrease in filtration by looking at the co-kernels. Oops. And so forth. And now this gives you a decrease in filtration. All right, so I want to apply this picture when I have a filtered complex. And I think this is the general thing that you do when you have a filtration is we look at the following complex, which is a large beast. So let's suppose now that we have a filtered complex. Then look at this direct sum of all these FPs. I'm not taking a graded quotient here. So this is a really large piece. I'm counting the same thing several times. And this overall piece. So this is a complex. Let me call this guy C. Probably I should have called this guy A. Let's do the other way around. Let's say that this is C, and let's call this guy A. So this A is a complex, and this is a graded complex. The degree is given by this P. So this is a direct sum of things like this. Each one of these FP is a complex, and the differential on each one of these FP is the same. It's coming from the differential in C that I'm just restricting to a subcomplex, FP of C. But now, this guy has a natural alpha, which is injective to itself, which what it does is it sends the FP plus 1 part of C to the FP of C. Which is just the inclusion. So this alpha, it's not a graded map on A. It decreases degree by 1. Okay? But I don't care about the grading in A. The important thing is that it's this very large thing, and then the summand of degree P, it's included in the summand of degree P minus 1. And that inclusion, I'm just denoting it alpha. Okay? So this is an injection, and then, well, what can I put here? Well, it has to be the, well, no, I'm sorry. What is the co-kernel of alpha? Let's write it here. So I have 0, A, alpha, A. And here I have A divided by alpha A, as I had before. But here, this is very simple, because now A divided by alpha of A in degree P, what I have is FP of C modulo the image of alpha, which is FP plus 1 of C. And this is the direct sum over all such P, so this is the associated graded to the complex C. And this itself is a complex where D is induced by the differential of C. But I only look at this guy modulo the remainder of the filtration. Okay, so now the situation is very nice. What we have is this gave rise to a spectral sequence where I have the homology of A, which is a very large beast, to the homology of A, which is a very large beast, but I didn't care about this. The E1 term came here and is the homology of this complex. And this is the E1 term. I'll keep these differentials here because they're very explicit. Notice that so we get a spectral sequence with E1 already being a homology of a complex. So we might as well just start the spectral sequence in E0. I define spectral sequences starting from R is equal to 1, but it makes sense to define them starting from any R. In particular, I can just define E0 to be this complex. Just that complex. And E1 is the homology of that, and E2 is the homology of E1, and so forth. So it just so happened that I constructed a spectral sequence, and in this particular case, we start from the homology of a complex, so I can call that E0. And it's associated graded to my original filtered complex C. Okay, so now what are the differentials? What is ER? What is ZR? And what is BR in this particular picture? So now alpha is very explicit what it is because it's just the inclusion. And so alpha is just given by this, and it's just an inclusion. But I want to be careful. I want to now keep track of the degrees that I had. Okay. So what I realized is the following. Is well, so let's look at what is ZR. Okay. What is BR in this situation? So let me quickly check what's going on. So ZR is going to be what? Well, I realize that my differential, so ZR is the kernel of the differential, but the differential decreases degree by R. Where am I? Right. I need to be careful on what is this the differential. So I haven't stated that. So we are in this situation where I started with this exact couple that came from a complex. And these two maps, this map was just the quotient map from A to map it to the quotient, but this map was the connecting homomorphism in homology. And the connecting homomorphism in homology decreased degrees in homology. Okay. So let's work that out explicitly. I claim something, and let me just claim the specific case of what it's going to be. So all of these complexes are graded. A is graded because it's a direct sum over every P. This associated graded complex is graded. So there's always this degree P which kept track of which space of the filtration I was going. It had nothing to do with this degree, homological degree on this complex, and it has nothing to do with the homological degree of this complex. It's just in which degree of the filtration I am. Okay? So that grading I want to keep track of. So I'm going to put here this degree P, and this is going to be this degree P everywhere. So these PEIs are going to be graded. Later on, I'm going to put this by grading, but for now, this degree only recalls which degree of the filtration I'm taking here. So these ZRs are going to be graded. All of these guys are now going to be graded. And, well, it is in the degree P of the filtration. it's on the degree P part of the filtration of the complex. But it also needs to be in the kernel of the differential. And the differential, oops, I need my alphas. Yeah. So it needs to be in the kernel of the differential, and the differential increases degree by R. How do I describe that? Let me describe that explicitly. Let me write it, and then we'll describe this in the E1 case, which is explicit. This is going to be P minus R. I'm sorry, this is increases degree. Plus R of C. This is plus F P plus Z. P plus R plus 1 of C. So I'm doing everything modulo P plus 1. This is why I'm looking in degree P. So my complex was in degree P was FP, and I'm looking at the degree P piece. So I divide by everything that is in degree P plus 1. And BR is something similar. It's going to be my F. So again, it's divided by this FP plus 1. And I still want it to be inside of the degree P, please. But then now it's going to be the image of the differential, so it has to be the differential of something that lived in degree minus R. So those are just the same formulas here, where I replace alpha by being just the inclusion of P plus 1 inside of P. So if you apply alpha R times, you're including P plus R inside of P, inside of FP. And those are this P plus R and the P minus R on these differentials. But this is of degree P. And ER, therefore, P is just the quotient of these two maps, which is just FP intersection the image of FP plus R, C plus P plus 1, divided this F, P, C, intersect D of FP minus R, C plus FP plus 1. But let's compute it explicitly, because it's very explicit. And this is how we start with. So let's look at our E0 is a complex. This is the graded complex of C. So the degree P piece is the degree P piece of this complex, and the differential is just the differential of C modulo FP plus 1. So how do you compute something here? If you give me an element V in F, P, well, in GER, you give me a class V in GER P, C. This is FP C divided by FP plus 1 C. So this V is the class represented by an element in FPC. D of V is an element in FPC, because the differential preserves this filtration, and then I define D of the class of V to be the class of dV, which is dV plus FP plus 1. So that's this differential here, and the homology is just the homology with respect to that differential. So that's E1. What is the differential of E1? So that's E1. What is the differential of E1? Oops. E1 is the homology of that complex. Is the homology of GERZ. And in degree P is the homology of that complex in degree P. So what is the differential of this complex now? And how do we compute that differential? And this is very simple as well. So we have the following sequence. Okay. So let's look at fp plus 1 divided by fp plus 2 of C. This sits inside, since fp plus 1 is inside of fp, this is inside of fp divided by fp plus 2. Everything is of C, so I'm not going to write this. Well, yeah, it's fine. And the quotient map, this is an inclusion, because fp plus 1 is included in fp. These two guys are the same. And the quotient is the quotient of fp by fp plus 1. So this is GER P of C. This is this quotient. I have nothing to say about this. And this is GER P plus 1. So now let's look at the corresponding, these are all complexes. So let's look at the corresponding homology in degree, at the corresponding long exact sequence in homology. So in homology, you get a map from the homology of this complex, which is E1 in degree P, and it goes to the homology of this complex. Which is E1 in degree P split plus 1. And the differential is just the connecting homomorphism. Remember, we define this differential always to be the connecting homomorphism when I have this exact couple that comes from a quotient in the category of complexes. So in particular, how do you compute that differential? So since it is the connecting homomorphism, how do you compute it explicitly? You explicitly compute d of v, where v is in E1 now. Well, now, an element in E1P, so perhaps I should be careful with how do I write this, because, well, in E1P. Before V was a class in C, and now I'm taking this V to be an element in E1, which is already a subquotient. So probably I should call it like this, a class V. So dV, like this. Okay, so I take V, a class in this E1P. This is a homology of GER PC. So in particular, there's something that represents this guy. So let's take some W, which is in the kernel of the differential for GER PC. Okay, so this is in the kernel of, I think I'm calling this guy Z2. No, Z1, sorry. C1 of GER PC that represents that V, such that the class, well, I should have called this V, such that this guy represents, sends this class V in homology. In other words, this class V is equal to V plus the image of the differential. But now itself, this V is an element of GERC, which is, so I forget the fact, I mean, this Z1 GERC is inside of GER PC. Because it's the kernel of the differential, and the differential is defined on the whole complex. So I can take this V already in GER PC. But the thing is that this is a quotient itself. So this is FPC divided by FP plus 1C. So this V itself is represented by an element that I'm going to abuse notation and call that guy V. But it's V1 plus FP plus 1C. So my element of V in E1 can be represented by an element V, which is in FP, C, plus the image of the differential D1 plus things that are deeper in the filtration. Now, when I apply the differential D to V, the fact that it was in the kernel of the differential here meant that this guy, the differential here, does not have an FP component. It lands inside of FP plus 1. That was the condition that D of V is 0 in this complex, in the associated gradient. But I can compute this guy, and this guy now is in FP plus 1. This is because dV, well, because V was in the kernel in Z1 of GERP, which is the kernel of the differential. And the differential is the differential in V modulo whatever I have in the P plus 1. So I know this happens. Okay, but I'm looking for this connecting homomorphism, and this connecting homomorphism should be something in GERP plus 1, which is that guy. So I look at the class of dV, which is dV modulo whatever I have in P plus 1, in P plus 2. And this is the differential. And then again, I still have to mod out by P1. That's because I'm passing from this homology. So this is the differential of the class V in E1. And now you can iterate this process. The process is absolutely trivial. For ER, the differential on ER is so the differential of an element, oops, sorry, I pick some V, which is in ERP. Then this V can be written as an element of the form, well, let me write it like this. The class, this class is because there's some V plus some BR plus something that is in P plus R minus 1. No, P plus R, which is what I care about, where V is in ZR. And, well, now you just actually, which is inside of FP. And now you just do dV plus FP plus R plus 1. And this is the differential of this guy. So what you do is you have your filtered complex. The first differential you compute is the differential, the usual differential in C modulo anything that is deeper in the filtration. So you have, if you grab your element V, it is in FP. You look at the differential of that guy, you mod out anything that is in FP plus 1. So okay, so that's your differential. Now you go one step further. So you computed that homology already, and now you grab your element V, it's in E1, it's in the homology of your filtered complex. Well, it is in the kernel of the differential because it's in the homology of the filtered complex, so you know you can represent it by something here such that it's an element in your original complex. When you apply D to that guy, you land deeper in the filtration by 1. So now you look at that term, modulo, so something in FP plus 1, modulo FP plus 2. And that's your differential. You compute the homology with respect to that differential. So now you get a new complex, E2. How do you represent an element in E2? You grab your element in E2. It's a homology. So you pick your element in the kernel of the differential. So you know there is something in the original complex that when you apply D to that guy, it lands in Fp plus 2. So you take the term of the form Fp plus 2 modulo Fp plus 3. And that's the differential. So it's a very explicit iterative process to compute differentials. And the thing is that the reason why this works is that it's typically much simpler to compute the homology of associated graded objects than the homology of the complex itself. So I can have a differential that is very complicated, that grabs an element in the differential of this thing is a sum of things. But if I am smart enough and I find a nice filtration for my complex such that out of that sum only one term survives, then I can probably compute the homology of the associated graded and make sure that this homology survives only in a few degrees. And then I don't care what are the other terms, because the homology of the next complex is going to have to be a subquotient of this homology, which if it was already 0, then it continues being 0. So now let's talk a little bit about degrees, which I wasn't careful so far. So I think here in this spot, there's something about the degree. So the connecting homomorphism here is true that it sends the homology of this guy to the homology of this guy. But the homology itself has a degree. So if this guy I look in degree whatever I want, this guy would land in degree -1. Okay? Now, if I keep track of this degree as well, then I have something that is bigraded. One thing was coming from the degree of the associated graded with respect to the filtration, and the other thing is coming from the homological degree of this C. And so this is a complex. This degree here means take the homology on degree whatever dot here is in this complex. And I was very specific when I defined a spectral sequence in what this degree should be. So I said that the spectral sequence should increase degree of one object and decrease the degree on the second degree. Okay, so I think I was careful that every time that I define this spectral sequence by this upper index P actually coincides with the upper index with the first index in our bigrading, but now I need to be careful with these two. And if I am naive and I put here Q, and here I put Q -1, then I'm going to have something like this here, which is unacceptable. Because remember that what I required is that the differential in ER goes from PQ to ER P plus R, Q minus R plus 1. And for R is equal to 1, this should be horizontal. So this Q should be stable, and this is not happening here. So the only way to shift this to make it happen, to make it work, is to add P itself here. So if I add P itself here, and I define this to be EPQ, then this is that. Okay. Did I get it right? P plus Q. I defined E1 PQ to be H P plus Q of GR P. No, that doesn't work. Let's fix this. This is not working there. What is true is always this, and this goes to this -1. So let's fix this so that when r is equal to 1, we need to go to degree. So the first thing to notice is the other way around, is my complex are, the differentials are increasing in this complex. So here is a +1. These are homological complexes, not homological complexes. The differentials in C are increasing. I was taking decreasing filtrations. And the differential goes from FP to FP +1 also as well. So these are increasing filtrations. So now I'm going to define E1 PQ to be HP plus Q here of GUR P. And this thing here goes to HP plus 1 plus Q, which is EP plus 1 Q by definition. So this is a definition, and this is by definition as well, and this is my differential in E1. Okay. So the upshot is that out of all of this discussion, if I have C, a filtered complex, I get a spectral sequence whose E1 term, the E1 term, PQ, is the HP plus Q of the associated gradient in degree P. So this is FP of C divided by FP plus 1 of C. And this spectral sequence converges to the homology of the whole C. I haven't told you what is the filtration in this last homology, but again, I'm not going to tell you. Probably I'll tell you next time. So a particular case of this is the case of a bicomplex. So now let C be a bicomplex. Okay, then I'm going to use that filtration. I'm going to use the filtration FP of the total complex of C. So let me call it C dot being the total complex of C. So C dot, it doesn't matter if it's lower, is the total complex of C. So this guy is the direct sum of I, j. So if I call this n, I plus j is equal to n, and j is bigger or equal than p of c I j. Let me see if I want to take that filtration. Yeah, I might be getting the wrong filtration. I might want it to do it by rows, but by columns. But anyways, so what is GUR C? Well, so here I'm going to be looking at things, sums like this, where the second guy is bigger or equal than p, modulo things where the second guy is bigger or equal than p plus 1. So then this GUR P is just the direct sum where the second guy is actually equal to p. So this is isomorphic to this complex here. But there's a problem, is that the total degree in this complex, in the total complex, so if I look at the component I, j, the total degree is I plus j. And if I look at this component I, p here, the total degree is I plus p. Sorry, the component of this as a complex is just I. So if I look in particular to the component IP, the total degree is I plus p here. And if I look at the component IP here, this as a complex where I am only looking at the first guy is in degree I. So what I need to do is shift this thing by p. So the component of this guy in degree n, so if I look at, well, yeah, so that's, when I look at Ci, P, in this complex shifted by minus P, is of degree I plus P, which is this guy here. So that's the associated grade. And I look therefore at the associated spectral sequence. So that's a filtration. This is the associated graded. And this is my E0 term in the spectral sequence. Let's make sure that I've gotten this minus correct. Okay, so P, I look at this complex, P shifted by minus P in degree n, and this by definition is this complex P in degree n plus P, in degree n minus P. And the component of degree n minus P here is C n minus P. The total degree of this thing is now in P C. This is the total complex in degree n. Well, this is the sum of, this is Cij that sum up to n and j is equal to p. So this has to be n minus p, which is equal to that. Okay, so this minus p is fine. So E0 is that associated graded. Let's look at the homology of that, which is our E1. So what is the differential in E0? So I look at E0 in some degree, so some component of E0, which is this. And the differential is the differential in the total complex restricted to this component. Okay? So the differential in E0 is induced from the differential in the total complex, and the differential in the total complex itself is a sum of the two differentials in the bicomplex. Is the sum of the horizontal differential plus the vertical differential in the bicomplex. Now, the horizontal differential, the vertical differential in this bicomplex increases the second component. Yeah, probably I screwed up vertical with horizontal, but it doesn't matter. So if I look at the vertical differential of this bicomplex, it increases this p. And increasing this p is 0 in the filtration because it goes to fp plus 1. So the vertical differential is irrelevant, and only the horizontal differential is what matters. And the horizontal differential in this complex is just the horizontal differential of the complex C dot something. So the homology of E0 with respect to this differential, which is just the horizontal differential, is just equal to the homology horizontal of the bicomplex. So I'm fixing the second guy, and I'm looking at only this degree here. Okay, so that's my E1. Now, my E1, remember I was looking at degree P. And degree P had this guy P here. And this homology is this complex. Okay, so now how about E2? Well, I need to look at what is the differential in E1. But the differential in E1 was computed how? It was, I look at something in E1, I represent it in this bicomplex. It should be in the kernel of the differential, so it should be in the kernel of the horizontal differential. And I take the full differential of such a thing. So that was the recipe to construct the differential of E1. I represent it, and I take the full differential in my filtered complex, which is C, and I see what happens. Okay, so when I take a representative here, I can represent it by something that is in the kernel of the horizontal differential, and the differential is just the vertical differential. So therefore, the homology of E1 is now, which is the homology of E1, is now the homology of this complex with respect to the vertical differential. And this is my E2. And now I just keep track of the degrees. So this was my P, this was my Q, this was P, and this was Q. And this is P and Q. Now how do I take the differential on E2? Well, this is tricky, because now what I need to do is represent this in this homology, look at my original C, which is the total differential, take the full differential of that. Whatever that is. But what I do know is that this came from a filtered complex, so I know that there is such a spectral sequence that starts at this thing. And this thing converges to HP plus Q of this total complex. But to have convergence, I need to find some finiteness condition that I haven't talked today, and I don't think I want to talk about this because, well, as a probably I'll talk next time. So this requires this convergence. I want to do this probably carefully. Convergence requires some finiteness conditions. For example, this C being the bicomplex being concentrated in one quadrant would work. We can do this with less, but that will work, and that's all we need now. And that's actually what I will do. So let's try to prove the original theorem that we set out to prove. So theorem. We have our C, our functor F to, we have our A, our functor F to B, we have our functor G to C, and we want to compute the derived functors. So there exists a spectral sequence the assumptions again was that I had an adapted category to A and an adapted category to B. Typically, this guy would be just injectives in A, and this guy might be larger than just injectives in B. But the condition is that F of this is inside of this. It takes a complex of injectives in A to something that is adapted for the functor G in B. And this F and G, of course, are left exact. Left exact. So then exists a spectral sequence whose E2 term, PQ, is HQ of, is RQ, G of RP, F of a complex A, and this is for any A in D plus A, that converges to R P plus Q of G composed with F of that A. So if I want to compute the P plus Q homology of a composition of a functor, then I can start by computing the P homology of one functor and then the Q homology of that complex, and eventually I will converge into this. So let's prove this. But this has a lot of applications. And the proof of this theorem it's interesting because it's the reduction to something that one would expect that is trivial. So the first observation is that let's look at what happens when F is the identity. So that A is equal to B. So when F is the identity, this spectral sequence, how does it look? Well, if F is the identity, the P homology of F is just simply the P homology of A. And I get the Q homology of G applied to the P homology of this complex A, and this should converge to the P plus Q homology, the P plus Q derived functor of G on this complex A. And this is already non-trivial to prove. So this is the case where F is the identity. So this is the hard part to prove. Let's reduce the theorem to proving that. So let's call this guy 2 star. So clearly this implies this in the case F is the identity. Okay, so how do I prove star from 2 star? So let's suppose that A, so remember that we have this equivalence. So how do we compute this thing here? This thing here was computed by, or the derived functor R of F was computed by replacing A by an object here in K of A in the derived category of that. So suppose that you have such an isomorphism. To some complex in this Ka. Then how do you compute this thing? Well, this is RQ of G of RPF of I. And this thing here is R Q plus, well, P plus Q of this G composed with F. So this is of A, which you do it with I. No, well, let's start with A. This is what I want to compute. Now, this by definition is what? Is take the derived functor of the composition, apply it to A. This is a complex in the derived category, and take the homology in degree P plus Q. That's the definition of this P plus Q derived functor of G composed with F. Now, how do you compute the derived functor of G composed with F on A? This composition was built out of taking H P plus Q of, you apply G composed with F to E, to I. Okay, so this is the definition of this RP plus Q of that composition, and that's how we compute it. Now the other side of this spectral sequence is RQG, RPF of A, But then RPF of A, let's do this again in 2 steps. So this is RQG of RPF of A, which you computed how? This is the pth derived functor of F applied to A, and this is the same thing as the pth homology of F applied to I. And now again, this is an object. So what is the qth derived functor of G applied to this object? Well, this is the qth homology of G applied to this object. Let me just of G applied to HP of F I. Okay. And now I claim that, well, since we had this guy here, that this guy holds implies that this guy holds. So both of these things are of the same form. This thing here is the P plus Q homology of G applied to something. This is the P plus Q homology of G evaluated in F of I. And this is the Q homology of G applied to the P homology of something. Okay? So this is equal to this side, where A is that complex, and the other side is equal, well, explicitly this. So if I prove this double star, then I can prove that I can prove star. And proving double star is not easy. We have 2 minutes. But we've already done all the work, and we've done all the work with detail. So we've already done the work when we proved the balancing of Tor without saying so. But when we proved the balancing of Tor, we did the following. Let's suppose, and now we're going to use the boundedness. So let's suppose that we have, and that's why I needed this bounding here. So we have a complex A0, A1, A2, and so forth. So what did we do when we proved the balancing of Tor? Right? We wanted to prove that we could take a resolution on one side or on the other side when we took the tensor product of two modules. And what we did is we resolved each one of these guys by taking an injective resolution. Oops, I think I'm doing this wrong. Dyslexic here. This is 1, and this is 1, and this is 1. And actually, this is 0, this is 0, this is 0, and this is 2, and so forth. C3 is 0, C1, 0, C1, 1. God damn it, I'm horrible. 0, 1, 1, 1, C2, 1, C3, 1, and so forth. So we proved that we could construct a complex like this with a bunch of conditions. So each one of these vertical arrows is an injective resolution. AI to CI dot is an injective resolution. Moreover, each one of these arrows here was exact, and it was split exact. Horizontal arrows they were split exact. And they were split exact, because this was an injective complex. It was an injective object in the category of complexes. We did it for projectives, but it was the same. So let me tell you what that means. And of course, we did this from the category of modules over a ring, the fact that those exist. For an arbitrary abelian category, it's non-trivial to prove that such a bicomplex exists, but we only need it for modules over a ring. Sheaves works. It's the same kind of situation. But the point is that this is what we constructed for modules over a ring when we wanted to resolve a module. So we out of this construction, what we ended up doing is that this complex here is quasi-isomorphic to the total complex of this C double complex. So that was the upshot of how do we prove the balancing of tau. So we constructed a double resolution of our complex by injective on each column, and it was split exact on each row. The fact that it's split exact on each row means that you have each one of these horizontal sequences gives rise to horizontal sequence induce each column is a resolution of AI. Each column I is a resolution of AI, but the exactness and split exactness of the horizontal rows say that, well, those resolution induce, the column induce resolutions of the kernel of the differential from AI to AI plus 1, just by restricting. You just take the kernel of the column. The image of the differential from AI minus 1 to AI, and therefore of the homology. And the reason we do that is, well, the fact that you get an exact sequence from this to this, well, that this is split exact is that you get this. You get the image of the differential in each one of these columns. It doesn't matter which one it is. Inside of your Ci, it doesn't matter which one it is here, P, into the, sorry, it's the kernel. Oh, that's fine. The image of the I into the kernel of the next one. Where here you just apply D. Oh, I'm dyslexic. I'm doing exactly the opposite. Applying D to something lands you in the image of the differential. Sorry, I'm taking some more time. So let's look at the column, the row P here. Then you have CIP. You apply D to that thing, and you land in the image of D in that row. And the kernel is the kernel of the differential. Now, this is injected. So this is, for every I, this is injected. You look at the long exact sequence in homology, and the homology of this guy is 0. This is an exact row. So the homology of this guy is 0. So this says that you get an isomorphism between the homologies. Well, you get when you look at the longest sequence in homology for this, you're going to realize that this column itself, it gives you a resolution of the homology of the complex A. So those are these statements that I have there. Let me finish the proof of the main theorem. So you look at that double complex there, and you use the spectral sequence associated to that double complex. So what you have is, first of all, that the homology of the total complex of C is the same as the homology of A that you're interested in. Okay, this is because you have this quasi-isomorphism. Homology is an invariant in the derived category, and this is because this is a quasi-isomorphism. Oh, the total of C is a quasi-isomorphism. Second is, we have a total complex of a double complex, so we have a spectral sequence whose PQ, E2 term is HQ of HP of this double complex. And it converges to that. Therefore, it converges to this, which is what I'm interested in. Okay, so I'm trying to prove to do this. Okay, so what I'll do is that, but instead of using that double complex C, which again is in injectives in A, so this is in KA, I'm going to apply F to that. So apply F to C. This guy is inside of KB, because that was my assumption on my functor F, that it sends these guys to this guy. So I can think of F of this as a resolution, not in injectives, but in things that are adapted. They are acyclic for G. So each one of these rows, now when I apply F, are going to be acyclic for the functor G, because they are in the adapted category for the functor G. And the arrows are going to be resolutions of F of these guys, of F of X. Sorry, the columns are going to be resolutions of F of X. Just apply the F to everyone, and F is left exact. So the columns are resolutions of F of A, and the arrows are exact for G, are in this adapted category for G. Okay, so now I have this, again, I have this spectral sequence for this double complex, whose E2 term is HQ of HP of F of C double. But F HP of F of C, where this guy is in the these are all acyclic. So this, look at this F HP here. The P is the horizontal homology, and the horizontal homology was given by exact guys. So this commutes with F. So this is HQ of F of HP of F of HP of C dot dot. Okay, so now let's read this with G is equal to F. So this side here says, let's look at HQ of G is equal to F, F of HP of my complex. This guy is quasi-isomorphic to the total complex of that. And this side here is HP plus Q of F of that complex, which is what this guy converges to. So we've proven this identity for a functor G, which is, I call this F. So rename F for G, and it's the same. So rename F to G, and we've proven this identity, which we know it proves the whole theorem. Okay. Sorry that I took 10 minutes. Next time I'll give it back. So the next thing I want to do is use the spectral sequence in a particular, in a couple of cases. I'm just going to compute the push forwards of opens and the push forwards of close and compute some explicit push forwards of shapes.